Now we are going to learn about the first derivative test. This is where things get really fun because now we are going to apply a lot of these definitions, but first we actually have to do more definitions. So let's get through that. So, all right, definition one, f function is increasing on an interval if for any two numbers x1 and x2 in the interval x1 is less than x2 implies that f of x1 is less than f of x2. Don't overthink that. This should be total common sense. So all of this means if x1 is less than x2, that means x1 is to the left of x2. And if f of x1 is less than f of x2, that means that y1 is lower than y2. So the function is increasing if as I move to the right, so I'm moving from, say, x1 to x2, I'm moving up. So I'm moving from f of x1 to f of x2. That should make sense. That's what increasing is. So think about as we move from left to right, the function's going up. Decreasing. So f is decreasing on an interval if for any two numbers x1 and x2 in the interval x1 is less than x2 implies that f of x1 is greater than f of x2. All that means is that I'm going down. So as I move from left to right, I'm going down. F is constant on an interval if for any two numbers x1 and x2 in the interval x1 is less than x2 implies that f of x1 equals f of x2. So as I move from left to right, I stay the same. That should make sense. All right, we've talked about increasing and decreasing intervals before as well, so this is not new. But we need these formal definitions because this is how we're going to use the first derivative test. So then we have a theorem. Given f is a function that is continuous on a closed interval ab and differentiable on the open interval ab. Same thing as with a lot of these that we've talked about already, the mean value theorem, Rolle's theorem, all that fun stuff had to meet these requirements, right? Another thing I want to point out that I don't think I've mentioned yet. So the reason why it has to be continuous on the closed interval but differentiable on the open interval is, remember, it's actually not differentiable at the endpoint of an interval. That doesn't meet our definition of differentiable. So that's why it has to be differentiable on the open interval, but continuous on the closed interval. So what we want to say though, so if we meet these requirements, then if f prime of x is greater than 0 for all x on the open interval ab, then f is increasing on the closed interval ab. If f prime of x is less than 0, for all x on the open interval ab, then f is decreasing on the closed interval ab. And if f prime of x equals 0 for all x on the open interval ab, then f is constant on the closed interval ab. These should make sense. We have already also talked about this. Think about when we were trying to draw the graph of a derivative from its function or vice versa. That's what this is telling us. Remember that if the derivative is positive, that means the function's increasing. If the derivative is negative, it means the function's decreasing. That should make sense because what does derivative represent? It represents slope. Slope is what it represents. So that's why if the derivative is 0, then the function's constant, because it would be horizontal, which is constant. Strictly monotonic. So a function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. Keep in mind that that means it is not monotonic if it's constant anywhere on that interval. So if I'm increasing, but then I'm constant, and then increasing again, that is not considered monotonic. But if I'm just increasing the entire time, so for instance, like f of x equals x, f of x equals x cubed, those would be strictly monotonic because they're increasing the entire time. If you throw a negative in front of any of those, then they're decreasing the entire time, which would also be strictly monotonic. Okay, so now our first derivative test. So we are given f is continuous on an open interval I containing some point c. C is a critical number of the function f on the interval I. F is differentiable on the interval I, except possibly at c, because remember that's one of the ways in which we can find a critical value is when the denominator of the derivative equals 0, so that might mean that the function technically is not differentiable there. But that's how we find the critical value potentially. then if f prime of x is less than 0 on the interval to the left of c, and f prime of x is greater than 0 to the right of c, then f of c is a relative minimum. So think about what that's saying, and this is really important that we understand this because this is how we're actually going to have to write our answers, which you are going to love when I make you do things like this. So this is saying, all right, f prime of x is less than 0. That means the function is what? It's decreasing. And then at c, we change to f prime of x is greater than 0. So that means the function is increasing. So picture you went from decreasing to increasing. So what happened at that point? So I'll even draw that. So I went from decreasing to increasing. So what is going on right there? That has to be a relative minimum, and that's what this is telling us, and that's what the first derivative test is telling us. If f prime of x is greater than 0 on the interval left of c, and f prime of x is less than 0 on the interval right of c, then f of c is a relative maximum. If f prime of x does not change sign at c, then f of c is neither a relative minimum nor a relative maximum. Okay, so let's look a little bit at this. So I'm going to draw a graph. Okay, so let's make this -1. I'm going to call this A. I'm going to call this B. And I'm going to call this 4. And now I'm just going to draw a curve. So let's do like, boom, open circle. That's what that is. Oh, actually, hold it. I want to change that a little bit. Sorry. I want to do like there. Okay. So I want to show that that's higher than that. All right. And this is just continuous. Like that's a really smooth curve. So, okay, what do we know? Well, we know that we have a critical value at A and at B. We also know that, so there and there. I know the function is increasing on the interval -1 to A and B to 4. I know the function is decreasing on the interval A to B. So because of that, since I went from increasing to decreasing, I know that I have a relative maximum at this location. Since I went from decreasing to increasing, I know that I have a relative minimum right here. These locations, though, would be nothing. So since this is an open interval, and this is an open interval, I cannot call those absolute extrema. If they were closed intervals, then I could. But here I have a relative maximum and minimum because my definition of the first derivative test, I went from increasing to decreasing and then decreasing to increasing. Another quick example, and I'm just going to draw a quick little graph, and we'll call this 1A and then 3, and let's do something like this. So in this case, I have one critical value at A, which in this case is going to be, there we go, a relative and absolute min. These are both nothing. So although that is a close, that's an n. Although this is a closed endpoint, it's still not the highest or the lowest, and it doesn't meet my definition of relative, because in order to be a relative max or min, it has to be on an open interval, and that is not. And then here I can say that this function was increasing on the interval a to 3 and decreasing on the interval 1 to a. So that meets my definition of relative min, and then it's also an absolute min because it happens to be the lowest point on the function. All right, now let's put this all together. Okay, so we're using the first derivative test to find relative extrema. That is the whole point of the first derivative test, find relative extrema. So we're going to do this a little bit together and a little bit on your own. So first, I want you to find the domain, first derivative, and the critical values of this function. Pause the video, find those, unpause when you're ready to move on. Okay, hopefully you recognize this is a polynomial. Domains all real numbers or negative infinity to infinity. First derivative, just do my power rule. 6x squared minus 6x. Awesome. Critical numbers. Set the derivative numerator and denominator equal to 0. There is no denominator, so just set the numerator equal to 0. I factor out a 6x, and I end up with x equals 0 and x equals 1 as my critical values. Okay. Now we are going to perform the actual first derivative test. In order to do that, we need to make what we call an increasing and decreasing chart. So I'm going to make a chart. I'm going to use the critical values as marks on the chart, and then I'm going to pick numbers that are between these critical values. So I'm going to say -1, 1/2, and 2. It can be any number you want. It just has to be, in this case, I have to be between 0 and 1. Here I can just pick anything larger than 1, and here anything less than 0. Now what I'm going to do is I'm going to plug those values back into the derivative, and I'm going to see if it comes out to be positive or negative. I don't care how large, I just care positive or negative. And so I can see that if I plug in -1 here, this is going to be positive, this is going to be positive. If I add together two positive numbers, that's positive. If I plug in 1/2, the whole thing is going to come out to be negative. And if I plug in +2, 6x squared minus 6x, that's got to come out to be positive. So what this is showing me is increasing and decreasing intervals. What I know is that if the derivative is positive, that means the function is increasing. Here it changed, so the derivative was negative, so the function became decreasing. So what happened at 0 was a relative maximum. Here then the function was decreasing, then the derivative becomes positive, so it's increasing again. So then at x equals 1 is a relative minimum. So now I'm going to actually find what are those values. So I know f of 0 is -1, and f of 1 is going to be -2. Okay, now this is the best part. This is the part that you are going to love. This is where we use what we call our derivative speak. And yes, this is a requirement, and you will lose points and get really nasty looks from me if you don't do this. So what we're going to say is we're going to say, since f prime of x is less than 0 on the interval 0 to 1, and f prime of x is greater than 0 on the interval 1 to infinity, at the point 1, -2 is a relative min. Now we're running out of time on this video, so I want you to move on to part 2, but I want you to try to use derivative speak to talk about the relative maximum, and then check that at the beginning of part 2.